How's it going, everybody? So this is going to be a little bit of a pun on the Green Book of quantitative finance. So what we're going to do is try to think about the goals of what a quant does in terms of the modeling department. Okay, so basically, I think there's about three questions that you should be able to answer as a quant. Um, you should be able to answer all three of these things if you were to give a Blackboard lecture, right? And if these three questions are sufficiently answered, then you have a successful model. So, um, and it doesn't matter really how the returns are, because I mean, for quants, like returns are just they're just numbers. I mean, they're just ones and zeros on a screen. We have number generators, like random number generators at banks, and just like mess with people's money all the time, because it's funny. So, like, we're not attached to these things. So, you can think about a state living on a smooth manifold. Okay, and prices, order books, volatility surfaces, liquidity profiles, all of those things are charts. They're coordinates and projections and nothing more. And we answer how these things change as flows on the manifolds or on the jet bundles of the manifolds if you have any respect for curvature or acceleration. And inference itself becomes just a simple map out of some compressed geometry. All right, and you can think about and by the way, like this is this is like a linear combination of like AI slop. It just inspires me. But the actual work like that I do, you know, I mean, I don't really feel like talking about it. So, but I'll give you guys this not mindset, if you will, but this approach to the problem solving, um, if you will. Okay. Now, the framework here, it doesn't care about your asset class. So the same objects themselves will describe rates, equities, and portfolios. And once you have some chart that is fixed and some projection um, value to value, like some projection valued evaluation of a manifold onto some real number that appears in your state machine. Because that's all computers are. That's all data is. It's just ones and zeros, and how we choose to represent them is extremely important. So these three questions, most normies, even people in industry, like industry quants, some people are just hyper focused on like one of these questions. Or, I mean, the most important question that everybody emphasizes is what can we infer from this? What can we infer from this model, right? Most people just start with a third question and they just be like, yeah, the first two questions are like empirical seasoning to our model, but that order is completely backwards because structure is going to tell you what can even be measured without contradiction. And then the dynamics is going to tell you which trajectories are real on the manifold. And then inference itself is a final garnish. I mean, it's easy. So it becomes almost trivial once how you choose to compress your data is honest. So all the signal processing, pricing models, alpha factories, trading systems, they're going to be subordinate to the sequence in the following demonstration, whatever, if you will. So cope with that. So you think first structurally about the market, and then you're going to want to think dynamics and then inference. So equivalently on a cipher, like basically if you want to decipher this through, we would talk about native jet bundles that stay intrinsic to the manifold, and talk about invasive jet lifts onto an ambient Euclidean space for computation, and then project that back like the civilized people. And then when you have symmetries that commute, symmetries themselves in the data, you can have the language. You can develop the language of abelian Lagrangians to give you God tier compression into orbit labels, and then quotient out the orbit or quotient out the extraneous things that normal people would just call noise. So no system is going to be allowed to skip this pipeline here, period, that we construct. Okay? So again, we're just going to think about jet bundles themselves that are evolving through time, K-jets, that then, allow us to define some dynamics, and then define some inference maps. Okay, and we'll go further into detail on how to think about this. But the first thing to really establish is that when you look at a market, right, the price as a vector, it's not a state. Two paths can agree on every price coordinate and still live in completely different jets. So liquidity curvature, inventory momentum, holonomy, all of these things, traditional models that equate state with price are quietly quotienting out the good stuff. And again, they call that remainder stuff noise, which is a classic, right? Oh, it's just noise, you know? Dynamics itself is not a loot box in Fortnite of, indicators, you will, of technical analysis signal indicators that just like randomly, may or may not give good statistics or whatever. At leading order, it's going to factorize into conserving symplectic and dissipating contact and coupling gauge pieces together. So you want to be able to compose vector fields on the manifold, and you do not want to stack features in the real numbers or in Euclidean space and pray that you're going to have orthogonality magically appear. You're just going to get a degenerate system. So what you need to do is, in order to even create some kind of learning or some kind of machine, some singular machine learning on this compressed state, you need to quantify the topology, spectra, and commutators as coordinates of z, not as some decorations on some neural net. Okay, and so that architecture is going to ignore z, and it's not some data-driven thing. It's solving the wrong problem with extra steps. That's kind of the problem, I guess, with all of these massive, wasteful computational landscapes that people have been building. So what we need to do instead is define the jet of the state in local coordinates on M. This is going to be K is going to be the simplicial neighborhood and the topology of the nearby states themselves. We want to quantify that, and then we're going to want to define the latent geometry, and the latent geometry itself is going to give us our regimes of the market and regime coordinates. Then what we can do is define an orbit space to reduce the dynamics under some symmetry and quotient out of symmetry that is within the data itself. And then we look at observable maps, so forecasts, edge, decisions, so the entire chain here. This is the name of the game. This is what I hope to accomplish in today's video. So yeah, I mean, I don't want to repeat myself. So the Blackboard quant, right? He's going to start always with a smooth manifold, not a price, okay? In some real numbers. And observations themselves are going to be projections, okay? And the ambient space, and here's kind of what I mean by a projection. You have some projection of X, some element on the manifold that maps to the real numbers, okay? And this evaluation itself is induced. And we can think about, and of course, where X is an element of this lower manifold. So the jet also of this manifold explains which deformations those charts are dynamically consistent themselves. So it's more of kind of a logical operation that is extremely powerful. I'm not going to waste more time on this. Let's talk about ambient space. So the ambient space, and by the way, I mean, of course, you're on YouTube, but you can pause the video anytime to read. The ambient space and realization of this ambient space is to embed some manifold into another manifold, with this new manifold being isomorphic to the real numbers in dimensions, where in becomes extremely large when compared to the regular mapping here with R little n. Okay, so you want to work intrinsically when possible, and extrinsically when you have to code something out. Okay, so this is just a way to think about native and invasive jets. So a lone point by itself is very useless. So you always want to lift to computationally. It's good practice to lift to jets, and intrinsic derivatives are going to be charts that are adapted to im. So and it's clean and it's canonical. And you can think about invasive jets as these differentials in ambient space and enforce constraints via the second fundamental form, where you have these normal bundles, or sorry, you have these this normal coordinate here, and then some embedded some properties that are enforced by this state itself. So in general, how you want to think about this is if you have uh, your state being x dot and x double dot, right? Where, by the way, the dots are the temporal derivatives of the state. Well, you can think about this as physics, right? I mean, it's just position, velocity, and then the curvature, right? So moving averages themselves don't magically become jets. That's another thing to keep in mind. Now, if you have jets with, again, for a native jet bundle and invasive jet bundle, you can formalize this further as a bundle of K jets with curves for some considerable, arbitrary amount in M that agree, that map to M that agree through order K intrinsically. Okay? And so with these logical agreements, you can then use the Levi-Civita connection of a chosen metric when the acceleration must be covariant. Now, an invasive jet bundle, again, is embedded in E, but one can use the J, the K jet of E itself with constraints from the normal bundle and give a second fundamental form here. And the invasive jets will be computationally convenient, but they will introduce extrinsic artifacts. Modeling is back. The modeling step itself is projection back to the tangent manifold in the intrinsic jet space. Okay. So for K is equal to 2, your state here again is just going to be a compressed notation here, and again it's just position, velocity, and curvature as these intrinsic and extrinsic type of having these extrinsic type of properties. Okay, the jet space itself turns basically these point clouds into these filtered simplicial complexes. So you can think of the Vietoris Rips and Czech topologies. There's also persistent homology that'll give us the idea of barcodes. But yeah, I mean, this is basically how you would want to visualize a jet. Essentially, as defining. Essentially, it would just define some kind of some state, if you will, that give us the positions, velocities, and accelerations in general, and then some kind of conformal transformation, if you will. Now, so for the Vietoris Rips complex, you can think of the persistent homology to give us long bars and quantify the real structure in the data, and then shorter bars that give us microstructural hope. And these coordinates will be all on Z, but so that would be the persistent homology. And you can see here, like, the birth and death of these particular topological modes are interesting, because the Hadwiger evaluations here are integral geometry, and the information geometry on the statistical manifold would give us these formalizations from how we're choosing to discretize our space and describe, the nearness of, these kind of primitive mathematical objects. This becomes really abstract, but we're basically trying to structurally. I'm just giving a bunch of options, if you will, for how to think about these windows or their jets, and in terms of these simplicial type complexes, as this epsilon gets larger and larger, you can get different faces of these simplices, and there's a way to actually quantify this with machines in a data-driven way. So you can think also about structural completeness. Um, so if you have Z, you can take a map um, here from the jet space, and the jet space is a function of time, and it'll be lossless on invariance in part, really in the dynamics and trying to describe the dynamics and make inferences. But how we can think about this as well is this kind of generalized. If we I'm just showing you that there's a generalized type of z-score that we have to describe statistical significance from the information geometry itself, as well intrinsically from whatever statistics that comes out of this, and yeah, Hadwiger evaluations as well. I mean, I kind of talked about this, but this is how we would choose to define the measures, and these observations becoming these functionals as volume and curvature as feasible sets in the state space. Okay, so we can now talk about the dynamics. So evolution itself is going to be a flow on the manifold with, it's not going to be some sequence of candles, that you typically would want to look at if you're looking at financial data. You'd be tempted to look at flow sequence of candles, but you really want to think about them as symplectic flows. So conservative pieces will live on the dual or the cotangent space with Hamiltonian equations, right? So that's how you can think about this. And the phase space volume is very sacred in these type of statistical systems that we want to describe. But we can start here and then perturb the symplectic basically core and geometry of what we're trying to achieve for Q and P, where Q and P are just these particular states. Q can be price, P can be the momentum, if you will, of the signed order flow of the market. But where things get, I mean, this is kind of like a physicist will look at this and know what I'm talking about, and anybody who's taken a differential equations class or anything would be able to instantly recognize this. But this is where things get interesting that I personally find super cool, is that when you have symmetry generators, say you have some symmetry that's encoded into the compressed manifold that we have, you can say that the systems is going to be abelian, and that the action will be able to factorize. This is more talking to the physicists, but there's something special that we have. It's called Frobenius' theorem, that leads us to integrable foliations and clean reductions, or the ability to have a clean reduction to an orbit space. And Noether charges themselves you can label the leaves of these processes, and this is where high dimensional ideas of chaotic systems will collapse into something tractable. You can think about the yield curve too, with like modes and volatility factors, sector rotations. Mathematics becomes extremely cool, really, with this kind of nuclear option of thinking about abelian Lagranges in orbit theory. So when you have an approximation, or when some symmetries approximately commute in the market, you get God mode compression. But when they don't, you have to carry the holonomy. So that's what will happen here. You'll carry the holonomy of the geometry, which is just, holonomy is just the transport of a. Holonomy. It's a very simple way of thinking about holonomy is just the Levi-Civita connection, defining a covariant derivative along some manifold and how much that arrow rotates. Okay. Now here's another thing that's very important in financial markets that is it's fair to mention, is rough paths. So rough paths and signatures for some real non-smooth trajectories, and contact geometry for these endogenous entropy market making bleed. Because when people are making markets, there's a thermodynamic thing happening, because the market is constantly in this combustible non-equilibrium system, So you have to think as well also as gauge connections is for these interactions between the basis risk. So here's your curvature. Uh, you would have like some curvature two forms or whatever to measure how badly your orthogonal factors are failing to commute. So again, and you can think this is a nice way to view the rough path theory for, just how you're going to decompose the tensor space of all of these integrals that like have all of this twisting and torsion. Um, and then also you'll have like contact dissipation. So like the the heat of the medium of some, with respect to some how some probability distribution is choosing to evolve. And simultaneously being aware of like entropy transfer itself. Um, this is contact geometry. I mean, there's no avoiding it. So, and you would then have to define a new quantity as some cumulative dissipation or irreversibility of the market itself, of something happening and some crash happening, and you have some bimodal fracture in your distribution, something like that, right? All of these observables. I'm really getting into the observables themselves, because that's what people see, right? That's what we when we see a nuke, right, or we see a rocket blow up, like you know it's hard to pin down exactly what it was that was the cause of it, but you know that's kind of what's happening here. The contact structure is going to be able to endogenously um derive that. So gauge connections as well um are important, but those things get developed much later. So how we can think about this as a connection for the gauge, as for a gauge connection on a bundle, or the connection one form on a bundle over M has a curvature where the parallel transport around a loop, um, gamma is going to return a holonomy, and the non-zero holonomy means that there's some factor definition that cannot be glued without transition. All right, and so here's like kind of a cool graphic of how to think about gauge coupling themselves. Um, and yeah, I'll just leave it at that. The dynamic map of completeness. So again, this always goes back to the flow. So we have some compressed geometric state that we dealt with in the first part, and this flow here will then allow us to describe the set of observables, um, and it'll erase persistent classes that has been carried um, within the state being described itself. Okay. Now, did I miss anything? Okay, let's go to inference now. This is the part that people, you get paid for. I mean, I'm going to be really quick about this because it's really not that complicated. I mean, it looks like it's super complicated, but it's not. You predict basically Z, right, from raw, not from raw ticks, but you're going to predict from this compression, and you have these maps on geometry themselves, and there's admissible architectures that will be able to factor these things and give generalizations of a geometric statement rather than some hope that is going to do this. Okay, so you'll look at statistical manifolds. You'll look at Fisher-Rao inference. These are important. Basically, I mean, these these themselves are pretty much well known in the industry already. So I mean, it's not really that interesting. But you can describe geodesics and loss manifolds and all of these things. But what I think is really interesting is singular models. Now, singular learning theory. Real models themselves are singular. And you can use something called a log canonical threshold lambda. And what this allows us to do is to have smaller lambda to get better generalizations. And it is a real log canonical threshold. It's a purely geometric triumph over parameter counting every time. You have like all of these massive ensembles of parametric models for these Bayesian inferencing models, and like it costs a lot of money to do, but the geometry itself is going to beat parameter counting every time, and it's cheaper, and the complexity penalty uh, becomes in the dimension of theta over 2, um, where theta itself, and by the way, regularity and singularity. I talked a little bit about this in the Discord as well, but regularity and singularity have to do with uh, basically the smoothness of some data, and the geometric data will give you those things. Okay. Um. So yeah, and then you can basically define these particular invariants, and the neural nets themselves will just read from the neural nets themselves will just read from uh, some J mapping to K to Z, but cohomology can also catch the global obstructions to this, and spectral theory on Laplacians can give regimes and timescales for free. So that's another thing that's very important to think about. And lastly, I mean, geometric prediction itself, because first of all, you can define learning on this manifold itself. Capacity control is this geometric type of quantities that allows us to preserve persistent classes under the flow. But really, prediction itself is a geometric thing, right? And you can forecast some curve by just integrating this or its stochastic lift with some function out at the end, and the quality will be judged by the Lipschitz constraints of f along the geodesics, right? And Lipschitz constraints, constants. Lipschitz constants really are just upper bounds and lower bounds that have been estimated, particularly with whenever you're dealing with these types of function spaces. So linear blends of past prices are chartwise shortcuts, and you can they're only going to be valid when your compressed data is going to be affinely embedded in real dimensions, or in Euclidean space, and the diffeomorphisms are approximately linear for the horizon considered. So there's very rarely the honest regime for inventory or volatility. And so the forecast just becomes a geometric segment in the latent space itself, right? So it just comes out very naturally. And of course, there's the cohomological inference as well. I don't really need to go into that, but these are other things that could be explored from the latent geometry. And of course, these graph Laplacians, you have gaps between these particular modes within the neighborhood. Those can also have predictive power. Now, it just goes back again to structure, dynamics, and inference. And that's it. That's the simple physics grade modeling for markets. And this is kind of, you guys want to join the Discord and be a part of the conversations behind this. I don't promise that this YouTube video is going to be up forever because it might take off. But this is basically a financial physical modeling for markets. So we have manifolds, jets, symplectic reductions to hopefully get approximate symplectomorphisms in our state machines that then define contact dissipation. We also have gauge theory, persistent homology, singular learning. All of the heavy artillery is now pointed at profit and loss. So traditional quant finance has spent like 20 years stacking features and hoping for the best. But what we're going to try to do is just get rid of that entirely. And the geometry itself was always there. Now what we need to do is just think about the cipher itself. And that's about it. So this is the formalization. This is the formal kind of pitch, if you will, for the black book of quantitative finance. And yeah, last thing I have to say is build.